Keyword search breaks when users use synonyms. Vector embeddings fix this by mathematically encoding the meaning of words into a coordinate system where similar concepts sit physically close together. Enable the vector extension by executing create extension vector. This command integrates vector operations directly into the database engine and allows for seamless semantic operations across your existing relational tables. Add a vector column to your table by specifying the number of dimensions. For example, use vector 1536 to match the output size of common large language models. Vector dimensions must be fixed at the column level. If your model produces 768 values, the column must be defined with that exact size, or the database will reject the inserts. Insert vectors as strings formatted with square brackets. The database automatically casts these strings into its internal vector binary format for high-performance storage and calculation during future search queries. The minus sign followed by a greater than sign calculates the Euclidean distance between two vectors. This metric measures the straight line distance and is ideal for data where the magnitude of values is significant. Use the less than sign, equal sign, and greater than sign for cosine distance. This operator ignores magnitude and focuses on the angle between vectors, which is the standard for most text-based semantic search applications. The less than sign followed by a hash symbol performs a negative inner product calculation. This is typically used for maximum inner product search when your vectors are not normalized to unit length. Find the closest matches by ordering your results by the distance operator and applying a limit. This retrieves the top candidates in descending order of similarity based on the query vector provided by your application. Without an index, the database performs a sequential scan, calculating the distance for every single row in the table. This becomes prohibitively slow once your dataset grows beyond a few thousand records. Indexes for vectors use approximate nearest neighbor algorithms. These trade a small amount of accuracy for massive gains in speed, allowing queries to return in milliseconds even across millions of rows.
The inverted file with flat compression index works by clustering vectors into groups called lists. During a search, the engine only checks the most relevant clusters, ignoring the vast majority of the data. When creating an inverted file index, you must specify the number of lists. A common rule of thumb is to use the square root of the number of rows for optimal partitioning efficiency. The probes parameter determines how many clusters are searched. Increasing this number improves the accuracy of your results, but increases the processing time required to complete the query. Inverted file indexes require existing data to train the clusters. If you build the index on an empty table, the clustering will be suboptimal as you add more data later in the process. The hierarchical navigable small worlds index is currently the most popular choice for high performance. It builds a multi-layered graph where the top layers provide fast navigation and the bottom layers provide precision. Search starts at the top layer with long-distance jumps between nodes. As the algorithm moves down through the levels, it narrows the search area until it finds the closest neighbors at the base layer.
Hierarchical graphs are stored entirely in memory for maximum speed. This means you must ensure your server has enough random access memory to hold the entire index structure to avoid disk swapping performance hits. The M parameter defines the number of connections for each node, while EF construction sets the search scope during index creation. Higher values lead to better recall, but slower index build times and higher memory use. Combine vector search with traditional where clauses to filter results by metadata, like category or date. The database optimizer determines whether to filter before or after calculating vector distances for maximum efficiency. Create partial indexes on specific subsets of data to save space. For example, you can index only active products or recent articles by adding a where clause to the index creation command itself. Use explain analyze to verify that your queries are using the index rather than falling back to a sequential scan. This command provides a detailed breakdown of the execution time and index hits.
The halfvec type uses 16-bit floating point numbers instead of 32-bit. This cuts the storage size in half and speeds up calculations with minimal impact on search accuracy for most models. Use the sparsevec type for vectors where most elements are 0. This storage method only records the non-zero values and their positions, significantly reducing the storage footprint for high-dimensional keyword-based vectors. Bit vectors store each dimension as a single bit. This is extremely efficient for binary quantization techniques, where you only need to know if a value is positive or negative, resulting in massive performance gains. For bit vectors, use the Jacquard distance operator, represented by 2% signs. This is perfect for comparing sets of binary features, where the overlap between active bits determines the similarity score. Hybrid search combines full-text search with vector search. This approach captures both exact keyword matches and semantic meaning, providing the most robust results for user-facing search bars in modern applications.
Merge scores from different search methods using reciprocal rank fusion. This algorithm normalizes rankings from both text and vector queries to produce a single unified list of the most relevant documents for the user. Generate embeddings in batches at the application layer before sending them to the database. This reduces the number of round trips and allows you to utilize GPU acceleration for the vectorization process more effectively. Always validate that your embedding process returned a valid vector. Inserting null or empty vectors into an indexed column can lead to unexpected errors or degraded search performance in certain index types. Keep an eye on memory usage and input-output wait times during heavy indexing operations. Vector indexing is CPU-intensive and can starve other processes if not properly managed with resource limits. Increase your shared buffers and work memory settings to accommodate large vector operations. The database needs sufficient workspace to perform the complex sorting and clustering required for building hierarchical graphs. Regularly run the vacuum command to reclaim space from deleted or updated vector rows. For inverted file indexes, you may occasionally need to re-index as the data distribution shifts over time.
Speed up index creation by allowing parallel workers. Configure the max parallel maintenance worker setting to utilize multiple CPU cores when building large HNSW graphs for existing datasets. Normalize your vectors to unit length at the application level. This allows you to use the dot product operator as a faster substitute for cosine similarity, since the magnitudes are all equal to 1. Implement database constraints or application logic to ensure every vector matches the column dimensionality. Mismatched vectors are a common source of runtime exceptions in production semantic search pipelines. Measure search quality using precision and recall metrics. Compare the approximate results from your indexed queries against the perfect results from a sequential scan to find the best balance for your users. Major cloud providers now support pgvector in their managed database services. This makes it easy to deploy scalable semantic search without manually compiling extensions or managing low-level operating system dependencies. Vector queries can be resource-heavy. Use connection pooling to manage the load on your database and prevent spikes in memory usage from overwhelming the server during high-traffic search events.
Libraries like PostgreSQL 3 have native support for the vector type. This allows you to pass NumPy arrays directly into your SQL queries, simplifying the bridge between machine learning models and storage. For JavaScript developers, the pgvector library provides easy integration with the standard PG client. You can store and query vectors using plain arrays, making semantic search accessible to web application backends. Migrating from specialized vector databases to pgvector reduces infrastructure complexity. Keeping your relational data and embeddings in one place simplifies transactions, backups, and data consistency across your entire system. The extension continues to evolve with new index types and optimization techniques. Staying updated with the latest versions ensures you benefit from improvements in distance calculation speed and reduced index build times. Success with semantic search requires selecting the right embedding model, choosing the appropriate index for your scale, and carefully tuning parameters like probes and connectivity to meet your specific performance requirements. You now have the technical foundation to build production-grade semantic search. Start by profiling your data, implementing HNSW for speed, and layering hybrid search to provide a world-class user experience.